whether you want to keep these nano seeds, or if you want to control, or if you want to transform or transform one morphology to another morphology simply by adding these seeds on water. So other case we can also functionalize. Okay, so you can take a C60 molecules and then it's a ferrocene molecule. Then you can make it a liquid-liquid interfacial preparation. So that means this is C60 saturated solution and ferrocene, which contains some amount of ferrocene molecules. And the moment if you add isopropyl alcohol or any alcohol, you can still make a sheets. But these sheets are completely, these sheets are always also contains the ferrocene molecule. So that's what here you could see. This is a sheet. So we have did mapping, transmission electron microscopy, EDAX mapping. You could see this is a carbon atoms. So this is a iron atom in the sheets. You could see the exactly this iron is uniformly dispersed through the sheets. So that clearly indicates that so these ferrocene molecules are incorporated inside the sheets uniformly. Okay. So we have also studied some of the interesting parameters like how this light absorption varies, how this charge transfer takes place in this material when you have a C60 alone or if you have a C60 FC nano sheets. And then the other side we wanted to align these nano rods. Okay, so we put a long-wear blood-jet film. So simply what we have done, we have taken this long-wear blood-jet. Over there, we injected this C60 nano viscous, and then we'll apply some pressure so that we can bring the nano rods are very close. So this is maybe a one-day process. For this, since we cannot apply too much pressure, so slowly this LB trough has to be used. So it's after a day, you could see there is some particles over there. As I told you, this C60 has highly hydrophobic in nature. So some of the tubes is broke, and then there's these are the some debris of those broken C60 molecules. But essentially, what we wanted to is the nano rods or the nano viscous has to be aligned in one particular direction. So this, when you align this nano viscous in a particular direction, how the conductivity varies. So ultimately, this idea is use this nano viscous in electrochemical applications. So that's why we have done these experiments. But what we have observed, when you change the size of the nano viscous, the resistance also changes. Okay, when you reduce the size small and small, the resistance also coming down. So when you align these nano rods in a particular direction, then you could also have conductive film or conductive nanostructures that could be used in electrochemistry. So this is actually still it's ongoing since a lot of work has to be done. So the other side, we wanted to incorporate some metal ions. Okay, so the earlier case we put in the seeds ferrocene molecule. Instead of that, what we thought we can put some ferrocene, that iron containing material or any metal oxides to make a metal oxides. So this case, I think we use ferric chloride. So we made a tube. So here you could see this is a tubes are very small in size. So we can, that's why I told you in the beginning, when you change the aspect ratio of the solvents, you could also change the nature of the tube size. So when in the moment if I add some ferric chloride and then this is a small rods has been formed, you could see when I do the mapping, here this is a carbon mapping. So this is iron mapping. You could see the iron material is uniformly dispersed again. So the other side, we also wanted to put nickel, but nickel case, what we got is instead of dispersion, these nickel ions get agglomerated and then get reduced by this reducing environment in the solution itself. And then we could see this metallic nickel particle. You could see here that there is a spots. Okay, here this area you could see. If you enlarge it here, you could see this particular one. If you expand more, then you could see this is a nickel lattices. Okay, so this shows that this it is not simply dispersion of these metal ions. There is a lot of chemistry involved in this, but things has to be studied. only people are working on this area. Is not much, but not much explored so far. Fortunately, unfortunately, these C60 molecules are too expensive. So this 1 gram is close to 50 to 60,000. That may be the another reason why this was not much explored. So we also wanted to make it this C60 tubes is, I told you, the as a template. Okay, I told you that sometimes before, this walls is made up of C60 molecules. The C60 is soluble in some solvent. So the idea is to make some metal oxide precipitate inside the tubular structure and dissolve these C60 molecules in the solvent. So once you make a C60 wires or tubes, you cannot simply dissolve it, since there is a bonding in between the C60. There is a van der Waals attraction between the C60 molecules. That's why this nanostructure exists. But if you want to make it dissolve, you have to apply a small amount of heat, but that will not damage or decompose the C60. That will only weaken the van der Waals forces between the C60 molecules. So because of this, you could able to dissolve this. So here, what we wanted to make a C60 nano viscous. You can do it in a two-way. One, you can dissolve in some suitable solvent, or you can also do it burn away. That is, if you burn the C60 molecules in air, you will easily evaporate. Okay. So this is another route. So here you will lose the C60 molecule, whereas if you dissolve it, again this dissolved C60 molecule would be used again for the next preparation. So that is the idea. That means the template is not, it will not waste. You can reuse the template material. So again and again you can reproduce the nanostructures. But as I told you, you can control by controlling the C60 nano viscous, you can also control the metal or metal oxide wires or tubes. So by controlling this aspect ratio, by changing the solvent ratio, you could also change the solvent ratio of, you can also change the aspect ratio of your metal oxide tubes. So this gives a lot of flexibility. You can decide what kind of metal oxide you want, what is the thickness you want, and what is your length of your metal oxide wires is required. Based on that, you can design your template. And not only that, in most of the template, for example, if you take some alumina templates like geolites or some SBA15, you should use a strong acid or strong alkali. But here it's such kind of environmental issues will not happen. You can simply heat treat this material to 200 degree or 300 degree, and then you can weaken the forces between these, where you can weaken the C60 molecule, the force between the C60 molecules. Of course, within 200 degree or 300 degrees Celsius, your metal oxide, most of the case, nothing will happen. But there are some metal oxides that are very sensitive. So based on this, you have to select whether you should go for this method or this method for removing the template. So we also explored this. We wanted to use making a titanium dispersion. So this is another example where you can see this is a bare nanotubes. So when you do it for EDX mapping, then this is a carbon atoms, and then this is a titanium atom. Okay, so the titanium is once again is uniformly dispersed into the C60 nanoviscous. When I heat treat and then remove this carbon, I could see this is a carbon wires, titanium dioxide wires. You could see this that still this is a wire like TiO2, but it is made up of or combination of individual C60 crystals. Individual titanium dioxide crystals. Okay, so this, I told you there is a voids. So this voids, this TiO2 will get precipitated, and then this forms here. When I remove the C60 molecule, then this titanium dioxide particles get agglomerated, and then it will end up with the wire-like structures. So as you know, this when you have the TiO2 C60, I think I hope some of you remember that yesterday we were trying to activate TiO2 in the visible light region. As this TiO2 has a band gap of 3.2 electron volt, it will absorb only UV light. So here if you have C60 molecules, then this C60 molecules has the band gap of only 1.6 electron volt. Okay, that means it will well absorb the visible light. Okay, 700 to 800 nanometers, it will easily absorb the visible light. So this visible excited electron can be transferred to this conduction band of TiO2, where you can do the reduction reaction and oxidation reaction, depends on your interest. Okay, so there are some attempt has been, this has been already attempted by Professor P.V. Kamath. I hope many of you are aware. He is one of the editor of Journal of Physical Chemistry. So he himself has wrote a thematic article when I was working on this area. Then we wanted to use our previous structure before removing this TiO2. Whether this carbon nanoviscous containing titanium dioxide, whether it works for these particular applications or not. So that's what we have done using some gas phase isopropyl alcohol decomposition. So in collaboration with Professor A of National Institute of Material Science. So this is the decomposition profile of isopropyl alcohol in dark visible region as well as in the UV region. So the isopropyl alcohol will become acetone as well as carbon dioxide. This may be transformed to acetone, or if it is you go for a complete removal, then it will go as a CO2 molecule. So in a dark, you could see this is isopropyl alcohol is concentration is somewhere it is like this. When you put visible light, there is increase in the acetone concentration as well as very low amount of CO2. I can say almost nothing. Okay. Whereas in the UV region, the CO2 is increases, your acetone concentration is increases initially and then it goes down, because this acetone also may be reduced, oxidized to carbon dioxide with the time. So this UV region, this activity is very high because your base TiO2 itself is active. Whereas here the visible light, you know very well that TiO2 is not active. So only this activity comes from the absorption as light by C60, that electron transferred to your TiO2. So only this activity, because of this, what we have seen this previous slide. So because of this mechanism, so there is activity here. And then if you go for the other side, where when you use only a non-TiO2 nanowire, after removing these fluorine molecules, you could see this isopropyl alcohol concentration is stable, and then this acetone or carbon dioxide is changing this concentration very, very minimal. Whereas in the UV regions, the carbon dioxide is acetone is also increases and carbon dioxide also increases. So if you see the amount of carbon dioxide evolved is 1 weight percentage of, for the 1 weight percentage of fluorine loaded TiO2 is 17 and 333 in the visible light as well as the UV light. Here it is a 17 and here it's a 333. If we come here, it's only 1. That may be very, it's not a very significant number. So since there is no fluorine present here. So the other side, here is a 300 and 305. Okay, the 305 is comes here, but still this is lower than these values. Okay, when you TiO2 alone, you have only 305. When you have TiO2 with the fluorine, it's around 333 ppm per 0.1 gram of catalyst per hour. So this clearly insists that the fluorine has some role as projected by the Professor P.V. Kamath. So it will absorb the visible light, but it will transfer to the titanium dioxide, and then this titanium dioxide will go for oxidation and reduction reaction. But unfortunately, what we understood is this stability of the reaction is very poor, because here this holes form this TiO2 can also may oxidize the C60 molecules. So because of this, there are some remote chances for the stability of the catalyst. So the other side, we use the same technique for preparation of cerium oxide. Since the cerium oxide is one of the best catalysts in the fuel cells, we wanted to make it a small fuel cell by using the cerium oxide. So this is a cerium oxide nanowires which we have prepared using the fluorine nanoviscous as a template. So we can see there's a perfect crystalline, cubic crystalline material. of cerium oxide is formed. So this is a small cell fabricated in collaboration with AIST. So AIST Japan. So this nanoviscous they have used in the fuel cells, and then they have seen some there is some improvement in the performance, but still I think after some time this has been I think stopped. Activity has been stopped. So the other side, actually, so far we have seen that the two-dimensional sheets are one-dimensional nanorods, but here we wanted to explore this for the three-dimensional materials. So actually, still these experiments are, some of these experiments are going on. I don't want to go into the details. I don't know maybe how many of you may be interested to listen all these things. But here what we done is we made C60 cubes. So this cubes is made up of individual nanorods. There over there you could see some white parts. So this is a silver nanoparticles. So silver nanoparticles decorated nanorods. This is again further assembled into a cube. So originally I had only C60 molecules and fully the silver nanoparticles. Okay. So the silver nanoparticles, the C60 assembles first as a small rods. Over there the silver nanoparticles deposited. Again this system is arranged itself and then it forms a cube. So this cube is, you could see this kind of bricks, it's made up of individual nanorods. So this has been this got some wide applications in SCRS, since it has some nanoparticles over the material carbon surface, and then also it has been used in drug delivery applications also. So this is actually just ongoing research. So we wanted to correlate this all the observations. Almost last maybe 10 years we were working on this. We wanted to make it some chemistry or some conclusion about this. But we wanted to relate the solubility of the C60 molecules in the different solvents like toluene, benzene, or carbon tetrachloride. So it's soluble to correlate the nanostructures, but that was not possible. There was no correlation at all. And then we also explored the surface tension of the solvents, whether that plays any role on this nanostructures formation. And then we also looked into the polarity of the solvents. But even we try to relate the dielectric constant or density or vapor pressure of the solvents, which we are using for the different combinations. As I told you earlier, when you use the same solvent, the same C60 benzene, when I use isopropyl alcohol, I used to get a viscous. Then the same benzene, C60 saturated benzene, when I use a tertiary butyl alcohol, I will get a sheet. When I use the C60 saturated benzene, if I use N-butyl alcohol with some silver nanoparticles, then I will get a cube. So how to correlate this? So that's actually this intention of this particular slide is only that we wanted to correlate this solvent properties and then its ratio to the pre-desired nanostructures. But unfortunately, it was not successful. Actually, after seeing our research, there was one group that came into the presentation. So they have correlated the results with some other observation. If we have the solvents like one-dimensional solvents, and then if you have this kind of benzene-like solvents, or if you have carbon tetrachloride like three-dimensional solvents, then you will get a C60 sheets and wires or dots. But unfortunately, this was not applicable for all this observation which we have observed. So again, this observation got failure. So far, still people are working on this area. Since I move away from the group, and then the C60 is expensive for India, so I did not able to continue much on this. But still, we are working on some of the interesting aspects, that too in the fundamental levels. So I could summarize here. In the case of liquid-liquid interface, you can make a different kind of sheets. You can take. I think I did not present anything on here. You could make some small nano rods by having a different solvent ratio. You could also convert this one kind of sheet into another kind of sheets. You can also make cubes made up of C60 nanoparticles or C60 nanomaterials. On the other side, you can also make porous nanoviscous by choosing appropriate solvents. So this is maybe, I think with this I will end up with my first part. So if you have any questions, maybe I'm happy, or maybe even at the end of the presentation also I'm welcome the questions. If you have any clarification in this area, then maybe I'm happy to answer. Maybe another 10-20 minutes, I'll go into the other part, like how these carbon-based materials can be used in supercapacitors and batteries. So coming back to the energy storage or conversion, again you can see this is yesterday we have talked about hydrogen storage or hydrogen preparation, and then solar cells and fuel cells. The other one is batteries and supercapacitors. I hope you are familiar with the fundamentals of capacitors and batteries. The
Sir, we'll
major
have the
difference
questions
is,
session at the end of this session.
yeah, sure, no problem. Yeah, I'll continue. Yeah. So the other side, if you see this, this is a major difference between the capacitors and batteries. I hope you might be familiar. The power density of your capacitors or supercapacitors are very high, whereas the energy density of the batteries are very high. But the batteries are suffer from poor power density, or these capacitors are suffer from poor energy density. This factor is so important. So to understand this difference between the various energy storage devices, maybe I will give you one more slides to show you how this energy density and power density affect. So this is a simple diagram of lithium-ion battery, how it works. So you have anode, you have cathode. So in between you have the electrolyte. So generally this lithium-ion will move from your cathode to anode as a lithium-ion solvated by the electrolyte, and then this electron move through the external circuit. So here there are different cathode material have been used. I hope Dr. Raghupati might be told you of all these cathode materials. So the anode material, generally graphite is used. But there are a lot of research is going on to improve the capacity of your anode materials. Generally graphite, which has a theoretical capacity of 372 milliampere hour per gram. So in addition to this, there are other materials, LTO, lithium titanium oxide is used. So these are the two materials currently in market. So all the commercial cells comes with this either graphite or LTO. So these are the other materials has been projected for future applications like graphene or silicon or tin or nanomaterials or metal oxides or sulfides. So I just quickly give some examples which we have done several years before, where we have used tin sulfide decorated graphene sheet and tin oxide based graphene sheets. Okay. So tin sulfide, I don't know, anyway, I'm not going to touch anything on this part. I'll just do only on this part, the tin sulfide decorated graphene sheets. So the tin sulfide has this kind of structure, so it's a layered structure. Okay, the three layer of sulfur and tin and sulfur. This is a sulfur, the sulfur, tin and sulfur atoms. So this is one unit, and then there is another unit. So these units are, there is a layered structure. Okay, so this as adjacent sulfur layers are bound by weak van der Waals interactions. So the enhanced guest accessibility. So because of this, you can put some guest molecules inside. The poor electrode kinetics and the low electrical conductivity of these materials